Question 3a. Under what circumstances does conservation of momentum apply? Well, this could be regarded as a bit of a trick question in that conservation of momentum applies in all interactions between objects. Part B. A tennis ball, mass 58 grams, is served towards a player at 42 meters per second. Calculate the ball's momentum. Okay, so for part B, we're going to use the momentum formula. Momentum P is the mass times the velocity. Now the mass given is 58 grams. And I have to be careful because I need that in kilograms. So, as you know, there's 1,000 grams in a kilogram. So I'm going to multiply by times 10 to the minus 3 to get it into kilograms. And then multiply that by 42. So, 58. And then I'm going to use the times 10 to the x button on the calculator, and it's minus 3. And then I'm going to multiply all of that by 42. The answer comes out as 2.436. But the question was given all in terms of two significant figures, so I'll give the answer to two significant figures as well. So that is 2.4 kilogram meters per second. Part C. The player swings her 0.25 kilogram racket towards the ball at 11 meters per second. Calculate its momentum. So this seems very straightforward. We use the same formula. In this case, the mass is given directly in kilograms, so I don't need to do any conversion. But I need to be careful when I look at the velocity, because the racket is going towards the ball, so it's going in the opposite direction. To show that, I use minus 11. Let's calculate that one. So 0.25 times minus 11, and the answer, again giving the answer to two significant figures, is minus 2.8 kilogram meters per second. Part D. The racket hits the ball, returning the serve at 15 meters per second. How does the racket move immediately after hitting the ball? Well, this is a conservation of momentum question. So the first thing I do is that I know it's a conservation of momentum question, and then I give the formula. So the formula is that m1u1, that's the initial momentum, plus m2u2, again the initial momentum. I'll call 1 the ball and 2 the racket. And conservation of momentum means that that is equal to m1v1, the final momentum of the ball, plus m2v2, the final momentum of the racket. Some of these things I've already worked out, so we can apply them directly. So the mass times the initial velocity of the ball, we've already worked out up here. That is, the momentum of the ball is 2.4 kilogram meter per second. So I can use 2.4 for m1u1. The mass of the racket times the initial velocity of the racket, we already have worked out here. So I can put that directly in as minus 2.8. That equals m1 v1. That's the final momentum of the ball. We know the mass of the ball. We used that before as 58 times 10 to the minus 3. And the final velocity of the ball is given here as 15 meters per second. Careful again here, because this is being returned, so it's in the opposite direction. So we have to multiply by minus 15. And then we need to add the final momentum of the racket, so that's 0.25 times v2. It's v2 that we don't know, so we are trying to calculate that one. So let's just work this out a bit. 2.4 minus 2.8 is minus 0.4. We need to work out this term here, so let's get the calculator on that. So 58 times 10 to the power of minus 3 multiplied by minus 15, and the answer to that is minus 0.87. Plus 0.25 v2. I now need to move my numbers so that they're both on the same side. I have minus 0.4, and if I add 0.87 to both sides, so add 0.87 equals, so I'll add it to this side, and we already had minus 0.87 plus 0.25 v2. I'm adding 0.87 and subtracting it, so those two cancel out. I can now work out this sum here. So that is 0.47 equals 0.25 v2. To get v2, I need to divide by 0.25 on both sides of the equation. So I will do 0.47 divided by 0.25 is equal to 0.25 v2. Again, both sides of the equation divide by 2.25. I need to calculate this side. This side, the 0.25s cancel out, and we'll get v2. So 0.47 divided by 0.25, the answer is 1 point, and I'll use just two significant figures, 1.9 equals v2. So that's v2 equals 1.9 meters per second.